Okay, so we were talking yesterday about how these elements form ionic compounds. So let's go big picture, right? What is an ionic compound? Give me a raised hand. Sir? Right? So one element takes electrons and okay, they're trying to get 8, the magic number, the octet rule, right? So one element takes electrons, and what happens to the other one? It loses, it gives, right? So it's this taking and giving. It's not a sharing. Remember, sharing is covalent. That's the type we'll do next. Okay? The things that give away electrons, what charge do they become? They become positive, right? Because I'm giving away a negative, so they become positive. What do we call those positive ions? The cations. You got it. And then the negative ions, the things that take, what do we call them? Anions, right? Metals or nonmetals? Which one are anions? Metals or nonmetals, which are anions? They become negative. Nonmetals, right? Because these guys only need a couple of electrons to get that magic 8, right? Group 17 only need 1. Group 16 only need 2, right? So they want to take. Give me electrons. Yes, please. All right? Metals, they give off their electrons, right? And that's the vast majority of the periodic table are metals, right? Lots of blue up there. So yesterday, I showed you the video for sodium chloride. Remember the reaction? Dropping that little piece of sodium in the gas and big, boom, wow, bright light, lots of heat, right? So I wanted to show you, this is from your textbook, and they're showing you these are all the different ways you can represent this reaction, to model this reaction. This is like a whole half of a textbook all in one little diagram. I thought it was very solid. And sorry for the bad scan. It's right in the fold of my textbook. I didn't have it any other way, but I wanted you to see it up on the board here. So this first one, this is what we did yesterday, right? You can see this. Just a regular equation, right? Sodium plus chlorine. You see that it breaks down into its 2 ions, right? Sodium loses 1, so it becomes positive. Chlorine gains 1, so it becomes negative. And there was a huge amount of energy produced. Right, it would be these two. The charge of these two coming together has to be 0, has to equal 0. So because I got a 1 plus and a 1 negative, we're okay. Comfortable there? All right, that should be pretty straightforward. We roll. Are you going to let me do this? Oh, here it is. It's on the wrong side. Okay, we roll over here, and they show you the electron configurations, right? That sodium is a 3s1, chlorine 3s2, 3p5. So what happens is that 1 electron from that 3s in sodium comes over to the chlorine, so it makes it like argon. If you're looking at the PT, you see that argon is the noble gas right next to chlorine, right? So it added an electron, right? Chlorine takes, it becomes a negative ion, becomes an anion, and so it's like argon. And sodium, when it lost that 3s, is like neon. And remember, noble gases are stable, right? Everyone's happy if we're noble gas configuration. Make sense? Orbital notation is the next thing. And we haven't looked too much at these before, but I think this will help you to understand those orbital things. Remember we said that each sublevel has orbitals to it? That the s can hold 2 electrons, right? So those 2 go into 1 orbital. The arrows, they actually are called up and down. I didn't make this up. The way that they spin, that's the way they call them, up and down. And you have one of those in the 2s, 1 orbital, 1 in the 1s, 1 in the 2s, 3 orbitals in the 2p, because 2p holds how many electrons? 6, right? So therefore, if you pair them up, you get 3 orbitals. Make sense? Okay, so you see one electron is transferred from that 3s in the sodium. One electron goes over into that empty spot in the 3p. And so you see that that's gone now here. This sodium no longer has that 3s. But here, that 3p is full now.
But it's still...
Does that make sense?
Because the last one I wrote it as argon after it.
Sure. If you were to look at 1s, 2s2, 2p6, 3s2, 3p6, that would be argon's configuration. No, they're just showing you for configuration sake. Just if you're writing it as electron configuration, that would be argon's electron configuration. Yes, ma'am?
It doesn't become argon.
It does not.
It has the same configuration.
Electron configuration. Why does it not become argon? With a raised hand. Anybody answer that question for me with a raised hand? Why does it not become argon? What do you think, Jeff?
It doesn't have the same structure.
Okay, more details. You're correct. More details. The atomic number. Good. More details. Sir? Doesn't have the same number of protons. You're both right. I just wanted to have the more detail. It doesn't change protons. It still only has 17 protons. 17 protons is chlorine. Are y'all with me? That's the only thing that makes an element an element. Okay? The only thing that makes Nick is he has this number of protons if he's an element. Nickeltonium. I don't know. Okay? That's the only thing that makes him that element is a number of protons. The difference between him and Jeff is nothing more than a different number of protons. Does that make sense? Okay. Good so far? Okay, another method. Again, just keep on rolling down here. You got your electron dot structures, right? Where one dot comes from sodium and goes over to fill that missing spot in the chlorine. And notice that they become these ions, right? Sodium as a positive one, chlorine as a negative one. Sir? Yeah, in this case, because the energy you see is that light, the heat, that explosion that happens. So that's just in the reaction for us to say, hey, this produces some energy. Okay. Some reactions need energy, like to split water into hydrogen and oxygen. You need energy. You have to put electricity through it to make it split apart. So that energy would be on the other side of the equation. It's a good question. And last but not least, they talk about the atomic models. Right? So a total of 11 electrons, 11 protons for sodium, 17 electrons, 17 protons for chlorine. And then we change the number of electrons to 10 and 18. But again, notice, protons stay the same. The number of protons doesn't change with a chemical reaction. The only way protons change is with what kind of reaction? We talked about this already. Not physical. Atomic is close. A radioactive, right? A radioactive reaction or decay, right? That's the only time that number of protons changes. Do you remember which kind of decay it is? Right. Our alpha and our beta, right? Good. All right. So what I'd love for you to do. Oh wait, we're not going to do that yet. Sorry. Let's talk about, again, how these things come together. One more time. I want to put together calcium, and I want to put it with fluorine. All right? So let's do this, because you're going to do these on your own. You're going to do some practicing here in class. Calcium and fluorine. How would I figure out the compound that this thing produces? Walk me through. Tell me where I would begin with a raised hand. Talk me through. I've got lots of folks over on that side who are interested in helping me, and I appreciate that. Jump all the rest of you guys in here. What do you think, Dylan? Okay, I'm going to start with the PT. That's excellent. In particular, what am I going to look for? The elements, their configuration, their group numbers. Yeah, all these things are telling me the number of valence electrons. But first of all, how do I know this even makes an ionic bond? Bigger, so I'm pulling you back. Big picture. I know that we're talking about ionic bonds, so of course it's going to make an ionic bond. But how would you know? Because on a final, I'm not going to tell you. On a test, I'm not going to say, hey, this makes an ionic compound. How will you know? Non-metal to metal. Does that make sense? I look and I see metal, non-metal, ionic. It's really that easy, truthfully. Yeah, metalloids are special. We'll talk about them. They can go both ways depending on where it is and what it's reacting with. But certainly for metals and non-metals, you know ionic. Yes, ma'am? Right, you want to make sure that each of them gets their stable octet, the noble gas configuration. You're correct. It doesn't. They will always seek that balance point. Yep, you're correct. We good? Yes, ma'am. It's in the second group. So let's talk about that. You're right. So how many valence electrons does calcium have? 2. So what charge will it have if it becomes an ion? A +2. Good. And then you were saying fluorine has what? Chlorine's over here. Is in group 17. So how many valence electrons? 7. So therefore, what's its charge? What's its charge? It could give away all 7, but it usually won't do that. Hang on. Group 17. How many valence electrons? 7. So it needs how many to be happy? 8 is total. Well, how many does it need? 1. So therefore, its charge is going to be -1. Does that balance? It doesn't. Christina's like, well, Mr. Hess, what the heck are you doing? You with me? Is there a way that we could balance these things? What do you think, Dylan? Oh, you're saying, yeah, definitely. He's saying, agreed. How? What do you think, Berkeley? What if I just have another fluorine? If I have a second fluorine, does that balance out those 2 positives? It does. So are you comfortable when I put these together, my compound, what's its formula going to be? Well, its total charge is 0. You're correct. But the formula. Yes, sir?
How do you know which one you put for negative?
Remember that the non-metals are the ones that give away their electrons. So those will always be negative. Yes, ma'am? F2. You got it. That's how these 2 elements make a compound. Yeah, that's our ionic compound. That's calcium fluoride. Are you with me? Yesterday, all we did was simply use groups that were equal to each other, right? We just did +1 and -1, +2, -2, right? What I'm telling you is, oh, no. You can combine any of those things together. It's just the total charge must be what? 8 electrons, but 0 charge. You're correct.
Why is it -1?
Because it has 7 valence electrons, and it only needs 1 to be happy. So it takes on 1 more electron. Because it's taking on a negative. It's taking on an electron.
So then why is it positive?
Here? Because it lost 2 electrons. So now it has 2 more protons than it has electrons. So it's a 2+ charge. Okay? Yes, ma'am? They do. And it would have the same formula. Yeah. If I wanted to use calcium chloride with calcium and chlorine, it would be CaCl2. You could. You could. What we're doing right now is just making what we call binary ionic compounds. Binary meaning 2. Just 2 elements together. But oh, certainly. Yes. Yes. Sir?
So if it was like a group 15,
Uh-huh.
it would be 3 of those.
We can do a group. Let's do a group 3. So pick group 15. Pick one of them. What do you want? Nitrogen? Okay. So he's saying, what if we had And let's use a same group 2. So let's use magnesium. Magnesium and nitrogen. We cool with that? Mg is a 2 plus. Nitrogen is a 3 minus.
3 magnesium and 2 nitrogen.
Are you with me? I got to balance these out, right? Let me move this guy up here. This would be CaF2. Mg3 and 2. That's exactly right. Because I'm making 6, right? If I have 3 times plus 2 means plus 6 on this side. 2 times minus 3 is minus 6 on that side. This whole thing is 0. Well, you could say, sure. It's just saying having 2 of these together. So this is another N. Right? And what we're saying here is I've got 3 mg's. So I multiply instead of adding. Same thing, right? Oh, sure. Yeah. Yeah. Pick me 2.
Boron.
Okay, boron is what charge? Okay, so it's a 3 plus.
Carbon.
Carbon? Don't use carbon. Group 14s are tough.
Wait, oh, no. Okay. I started with the 13.
Yeah, let's not use boron. I mean, it works, but I'm trying to avoid the metalloids right now. Let's say aluminum. How about that? Aluminum is a 3 plus. And then how about oxygen? Is that cool? Oxygen is a group 16, so what charge? 6 electrons, 6 valence electrons, so negative 2. Good. Okay, I want to put these things together. Can 3 go into both of these numbers? Like, is 3 a common multiple of 2 and 3? No. Not 4, not 5. 6 is the lowest common multiple, right? So therefore, I need to make this into be 6 plus, right? I need to make this into 6 minus. Does that make sense? If that's the common multiple between these 2 charges? So how do I get this to be 6 plus? I need 2 of them, right? Al2, and oxygen needs 3. You got it. So this will be Al3 plus. Oops, just 2 of those. And then 3 of those guys. Yes? It would just be aluminum oxide. We'll talk about the naming. I'm not worried about that yet. We will talk about how to do that. Because there are special rules you have to follow and all that, yeah. Are you with me, my friends? I think you're there. I think you're there. Okay, try this. Try this. I want you to answer these questions. Yes, quickly. All right, let's jump into these problems and see what you got here. Sodium, what group? It's group 1, so valence electrons, how many? 1. Its charge is plus 1. Okay, so that's a plus 1. Nitrogen would have what charge? Negative 3. Good. Okay, because it's in group 15. So therefore, Na3N. And you don't even put the 1. We assume if there's a 1, you just leave it alone. Okay? Good. So Na3N, sodium nitride. Okay? Lithium and oxygen. Lithium would have what charge? Plus 1. It's again in group 1. Oxygen, negative 2. It's in group 16. So therefore, how would I combine these? Li2. Oxygen. No, we want to balance the charges. In this case, it happens to be that. Since this is a plus 1 and this is a plus 2, then yes, I need two of them. But it's not always that way. I know that's what you've seen these last two. It's only because these are both plus ones. Strontium. Strontium is plus 2, right? It's in group 2. Fluorine is a negative 1. So therefore, what's my SRF2? You got it. You see how that's different, Dylan? That this was a 2 plus and this was a 1 minus. So therefore, I needed 2 fluorines to balance out the 1 strontium. Okay. Whereas this was a 1 plus and this was a 2 minus. So therefore, I needed 2 of these to balance that out. And again, a 1 plus and a 3 minus.
I thought that whatever number goes at the top was the valence.
It's the charge. It's the charge. These are not actually part of a formula. That's why I wasn't writing them at first. So I don't want to confuse you. The formula is just as I've written them here. How about aluminum and sulfur? Al2S3. Because this is a 3 plus and a 2 minus. Are you with me? Group 1, what charge would group 1 have? Positive how many? Plus 1. Group 15, the non-metals in it. Group 15 has lots of things. But the non-metals would be what? Good. So if I want to write, if A and B are their elements, what would be the? You got it. Does that make sense? And again, those aren't actual elements, A and B. I'm just assigning them letters. Because it could be any element in group 1, any element in group 15. Make sense? Good. I hope you're comfortable here. All right, what I'm going to have you do is, and we were going to do this in class, but we spent too much time here, which is fine. You did some reading yesterday, and basically all of 7.2, after we got this little piece at the beginning, was about the properties, right? What ionic compounds are like. And so I want you, please, to just define and describe the properties. I think there's about 6 or 7 that are listed there in 7.2. And you'll write that, and we'll talk about that more on Monday.
Do we have to have partners then?
No, this will be just by yourself then. Yep, I apologize. Adios, my friends.